So the next topic we're going to talk about are the key methods in the ForkJoinTask. So remember, ForkJoinTask can be submitted from a non-ForkJoinTask client, and then once it's submitted, then it can do a bunch of other things that work in the context of the ForkJoinTask itself. And some of this will become a little bit more clear as we go through this in more detail. So we're going to talk here about the key methods in the ForkJoinTask itself, and you can see that ForkJoinTask has certain other relationships with other classes. It implements future, and then it in turn is used as a superclass for a couple of other classes that are very commonly used. So first thing to notice is the ForkJoinTask implements the future interface. So you can see that ForkJoinTask implements future. It's actually not that common to use the future methods in general with ForkJoinTask. The most common time it's used with ForkJoinTask is if you submit a ForkJoinTask from a non-ForkJoinTask client, and then you want to be able to essentially get the result. So that's the most common way that it's used. Instead, we're typically going to use other methods like join in order to be able to get the results from something that's submitted as a ForkJoinTask, and you'll see more about that in a second. So the three key methods on ForkJoinTask, and keep in mind that when these methods are called, we're running in the context of a ForkJoinTask running in the ForkJoin pool, rather than having it being submitted by a non-ForkJoinTask client. Now, again, that'll make a little bit more sense later. So the fork method is going to create a task that will run in parallel. So you fork it, and it doesn't block. So it arranges to execute this task asynchronously in either the current tasks pool, if you execute it on a ForkJoinTask that's associated with a particular pool, or in the common pool if you don't. So there's a couple different ways to do that. What fork does is it goes ahead and pushes the task onto the head of the deck that's owned by the current worker thread. So remember, we talked about non-ForkJoinTask clients. Non-ForkJoinTask clients are running outside the context. They're running in threads that are outside the context of the ForkJoin pool. And remember, they put it in this shared queue. And then one of the threads in the ForkJoin pool will take the non-ForkJoinTask client's ForkJoinTask, and we'll go ahead and start to do something with it. And so if that particular task forks, at that point it's now in the context of a worker thread running in the ForkJoin pool itself. And so what that'll do is that'll, under the hood, magically push that task onto the work queue or the deck of that worker thread. Now, whether it stays there to process or not is another story, but we'll come back to that in just a second. So that's what happens when you fork. Fork arranges to execute the task asynchronously in the current task pool or the ForkJoin pool's common pool. So that's what fork is doing. Fork is pushing something onto the deck of the calling thread. Join is typically also called, and when it's called, it's going to do various things, but the main reason it's typically called is you want to get the result of a computation that you forked when that computation is done. So after we fork, then at some point we're going to join and get the result. So that's forking and joining. And the way to think about this, this is a little bit unusual. It's different than the way that Java threads work with starting a thread and joining with a thread, in that when you call join, it blocks the calling task until the forked subtask is done, but it doesn't block the calling thread. The calling thread will actually kind of pitch in and do other processing using the so-called collaborative Jiffy Lube model, where when you call join, it'll run other things, and then when the task is done, it'll get the result and continue running. Something else that join does is it defines a so-called synchronization point. And this has a very interesting property called happens before. And we'll talk a lot more about happens before in next semester's class. But basically, happens before is used to make sure that once you join with something, the caches that are managed by the different cores on a multi-core processor are properly flushed, so all the threads will see a consistent view of memory. And we need to do this to make sure that any changes that have taken place in the thread that was running, that was forked in the background, are properly propagated to whatever thread is joining with this thing when all is said and done. And otherwise, you end up with something called memory visibility problems or memory inconsistency properties. I'm not going to spend a lot of time talking about this. That'll be a topic for great discussion next time. But just be aware that join also has this characteristic of being a synchronization point. And then invoke is basically like a fork followed by a join. So it'll perform the task and await any completion that's necessary, and it'll return a result. So it's basically a two-way call, whereas fork is sort of a one-way call. It starts things off and runs asynchronously. If something fails, if for some reason when we fork and join an error occurs, it'll throw some kind of exception to propagate back any problems that occur with the computation. So you can do something about that. So key point is invoke is a logically synchronous call. OK, so those are the key methods in ForkJoinTask. Again, what we'll see, I think it'll make a lot more sense when we start seeing how this is actually programmed. You'll see how fork and join work. And of course, your particular assignment number 3A is also using fork and join. And so you'll get a feeling for that. And the typical way it works is you fork a bunch of things off, as you do in assignment 3A, and then they all go and run concurrently, and then you come and you join with them, and when you're all finished, the computations have a single reduced result.